Okay, feel free to ask questions during the talk. I will be pleased to answer your questions. And thanks again for inviting me. And it's an honor to speak here, although virtually. So about Phanous, we are a research and innovation center, which is an R&D of an Iranian company, and we are trying to solve machine learning problems. We switched line to machine learning, and we now are working on machine learning. And this work was from the last year that we were working on optimization problems. This is a joint work with Salman Begi and Artin Tajdini. So the title of the talk is Time and Query Optimal Quantum Algorithms, which are based on classical decision trees. And I need to introduce some notations first. And these papers that I listed here are the ones that you can go and check and read more about this definitions and preliminaries that we need for this talk. And I'll very deep since I don't have. Okay, and once again, feel free to interrupt me and ask any questions if you want. Okay. Okay, we'll start with some basic definitions, and sorry if you know the definitions, but just to make sure that we are all. The first one is about the query. A query. Okay, let's assume that we're given a function f. And we want to compute the output of this function f on some input x, and we don't have implicit access to x. So in order to read the bits of x, we have an oracle that we can input the indices of x, and it outputs the value in that index. For example, let's say that the function f as and the input x is the string 0001. So we have an oracle that encodes this string, which we have it here, and we need to evaluate whether the answer to this question. It give you an algorithm for this. So I start from the beginning of the list, ask the queries this oracle 0 index. I mean first index. Let me. Okay. I ask the value of the index 1, and it outputs x1, which is equal to 0. And then the second bit, I ask the second bit, so the output will be 0 again. I cannot, I should ask another query, which is the third bit. Can you see what I write? And x3 is equal to 0. So I try not to write. I think you cannot see what my.
The writing is a little bit tricky to see.
Yeah, I don't know why, but okay. When we ask the last bit, which is the fourth bit, it outputs x4, which is equal to 1. And when we say this part, we can determine the answer to this question, which is yes, there is an index. The value of this function for x will be 1.
Leila.
Okay, so we have a classical.
Leila.
What?
Sorry, the sound gets interrupted. Maybe it helps if you turn off your video, maybe. Optimize sound. I don't know how.
Yeah, that's a good idea.
There's a menu to optimize for sound.
Okay, is it better now?
I don't know if it's.
I turned the video off. Is it better now?
I think so.
Can you hear me?
Let's try it for a minute. See if it's better now. Maybe don't turn off your sound.
Okay. Yeah. Do you hear me?
Yeah.
Okay. Is this sound good?
Yeah, let's give it a try. So maybe let's continue.
Okay. Let's see. Okay. So any classical query algorithm can be modeled using a decision tree. A decision tree is a rooted binary tree whose vertices are labeled with query indices and whose edges are labeled, and it has some leaves, and the leaves are labeled with the function values. So if we are given an input x, we traverse this tree using the value of the queries, and we get to a leaf, and that leaf determines the value of x for the value of the function for that input x. Okay, is the sound good now?
It's a bit better.
Can you hear me?
Yeah, we can hear you.
Okay, let's see what else we can do. If you can't hear me, can I can send you my presentation and stop the screen, and maybe you can share the screen and I talk from your screen.
It's better than before.
Do you think it's okay? Okay. So let's continue. If okay. So the depth of this decision tree determines the number of queries that we need to ask from our oracle, which is the complexity of this decision tree. So everything was classical till here. So let's switch to quantum query algorithms. In a quantum query algorithms, we first need to have a quantum oracle. A quantum oracle is still a black box that encodes some input x, and the input to this black box will be a quantum state, and the output will be a quantum state too. And in the input, we ask some index, and we have a register that outputs the query value for us. So we ask the input will be I and 0, and the output will be I, and the value of x and input on index I, which is xi. And we can query this oracle in superposition. So it may help to accelerate some of our classical tasks. Okay, and the quantum query algorithm is an alternation between two types of unitaries, UIs and OX. OXs are the oracles that we talked about, and the OIs are just unitary gates that are independent of X. And you can think of it like you do some computations, and based on the value of that computations, you do some, you ask some query, and then in UI, in U1, you again do some calculation. You again make another query and you continue until you find the value of the function by measuring some of the work qubits that you have. Okay, is everything clear till now? If you wanted to ask some questions, I will stop here.
And maybe,
Okay, so for
sort of
good.
You can optimize the video.
We don't want that, right?
Well, then maybe this thing goes better.
We want to optimize for sound.
And there is this thing, share computer sound. So you have this sort of window that where it says stop share. Can you hear me, Leila?
And I didn't have your voice, but now I can hear you.
There sort of is on the.
Did you say something about? Did you have a question?
No, but you can maybe optimize your screen. And there's also a thing called share computer sound. You see this floating window where it says unmute and start video, and where you also share in your Zoom.
We're looking at her screen.
Let me see.
It says more, 3 dots, and you see more. When you click on that, there's a menu, and then there is optimize screen share for video clip and share computer sound. Maybe you can click both of these.
Okay, let's try if you can find that. Maybe I stop your video. That will help. That may help.
But then you cannot do it when you stop the share.
Okay, is it better now?
I don't know.
Can you hear me?
Yeah, for sure. I think it's much better.
Okay. Okay. So can I continue now?
Yes. Maybe it's first.
Let's try this for a minute. Anyway,
okay, let me continue and
the
see whether it works better. Okay, okay.
This is worse. The sound is worse. There's an echo now.
Okay, so let me switch back to.
Maybe undo what you just did.
Okay. Sorry. Can you hear me now?
Yeah, there's still this echo.
Yeah.
Did you undo what you just did?
Yeah, I did it. I did it. I did.
Okay.
So you still hear an echo?
Yeah, a tiny bit. Maybe.
Okay, then what else I can do? Okay, just a minute. Maybe okay, disconnected the VPN. Maybe that helps. Okay, is it better now?
Are you on a VPN?
Yeah, I disconnected the VPN. Without the VPN, I couldn't connect to the Zoom.
Maybe that's causing.
Now I disconnected it. Is it working now?
We can still hear you, so you couldn't connect.
Maybe is it clear now?
Yeah. So yeah. Yeah. Go ahead.
Okay. Okay. Let's see if it works. So I will continue with the definition of the non-binary span program, which somehow characterizes the quantum query complexity of a function. Is defined as follows. It consists of a finite dimensional inner product vector space V and m non-zero target vectors, which are t0 to t sub n minus 1, which belongs to V, and some input vector sets, I sub j and q for all index j, and all values that index can make, which are from 0 to L minus 1, and the set of free vectors that we can freely use them. So what we want to do with the span program is to evaluate a function f, which is from f is from a subset of L to the n to m. So for every value of the output, we have a target vector, which is t sub alpha, and for every index of the input and every value of that index, we define a vector set, which I denoted by I sub j and q. Okay, we also define a matrix A. Matrix A is a collection of these vector sets. We put on which we call it A, and I should also put I sub free here as well. So for some input x, we define the set of available vectors by I of x, which is the union of I free and all of the input vectors that determines with the value of the xi's in our inputs. This is very similar to the binary span. The only difference is that we have L values for every input, and the target is not just one. We don't have just one target. We have m targets, and any of them is associated to some output value. Okay, I hope the definition is clear, because we need this non-binary span program as a tool to convert a classical query algorithm to a quantum query algorithm. Okay, a non-binary span program also has a complexity. To define its complexity, we need to first have a function f, and if we say that f, then we should have two witnesses for every input of f, which we call them positive and negative witnesses. The positive witness should determine whether we are able to build, I should be to t, sorry for them. So this is t sub alpha. We should say that we should determine that whether we can build T sub alpha out of our set of available vectors for x, which are I of x. So in order to show that T sub alpha belongs to the span of I of x, we need to introduce positive witness, which is W sub x, and we need to show that A times Wx is equal to T sub alpha, and we only should use the columns of A that are related to a set of available vectors. I mean, if the input x, let's say that x is equal to 0, 0, 0, 1. So if you have this input, the set of available vectors will be these that I determined with yellow color. So the first index is 0, so we can use these vectors here, also these vectors, and the last one is 1. Okay, sorry. So this is available too. So our positive witness can only use these vectors to build T sub alpha. Okay, this is the positive witness, and for the negative witness, we should say that T sub beta for all beta not equal to alpha does not belong to the span of I of x, which are the available inputs for us. So in order to show this, we define negative witness. This negative witness should be perpendicular to the space of available vectors, which is I of x, and it should be correlated to all of our T sub betas. And as you see, this is a firm condition here. This is a very strong condition, since we require it to have an inner product of 1 to all T sub alpha, T sub betas, and it's independent of which beta we choose. So it's not very easy to define a non-binary span program. But we could not relax this condition, and this is an open question whether you can relax this condition or not. So we can make it somehow dependent on the value of betas. Okay, and the complexity here is defined like this. We need to find a positive witness with minimum norm and a negative witness that it's inner product with all sets of available vectors minimized. The sum of the inner products, we should get this sum minimized. Okay, is the definition clear?
I think it's okay.
Okay, let's continue. Okay, we now go to the main result. Okay, what I need to do, what I want to do is to show that if we have two classical algorithms, the first one is a classical query algorithm that, as I said, can be modeled by a classical decision tree along with a guessing algorithm. And this guessing algorithm predicts the query answers for us. So if we have these two classical algorithms, we can design a quantum query algorithm that its quantum query complexity is equal to the maximum number of wrong guesses that this guessing algorithm makes times the classical query complexity of the classical algorithm that computes that function f. So as I said before, this T is the depth of the decision tree, which is the classical query complexity of our classical algorithm, and G is the maximum number of the wrong guesses that the guessing algorithm makes. And we somehow determine this guessing algorithm in our decision tree by coloring the edges. We color every edge by color red or black. If that edge is related to a wrong guess, we color it with a red color, and if it is associated to a correct guess of the guessing algorithm, we color it with a black color. So if we have a classical algorithm and the guessing algorithm, we can convert it to the decision tree, which is colored with the colors red and black. And if we have this, we can prove that the query complexity of the function f is equal to O of square root of this g times t. And this is only about the query complexity. In the work that I'm talking about, we prove it for the time complexity of this algorithm. So let's get into an example, the coloring for this. So in the OR function, a classical algorithm, a simple classical algorithm for the OR function is to start querying the indices by one from the first index. So I start with querying the first index. If the value of this index is 1, we evaluate the function and we say that f of x is equal to 1. If no, we go to this path and ask the second query and continue until we get to the leaf, to a leaf. If we go through this path, we say that f of x is equal to 0, and we didn't find any 1. So once we see the first one in our queries, we can determine the value of the function. So g, which is the maximum number of red edges that we see starting from root and traversing the tree to get to a leaf, g is equal to 1. And t is the height of the tree, which equals to n. So we can say that the query complexity of the OR function, the quantum query complexity of the OR function, is equal to square root n, which is a known result. Okay, let's go further. And what we did is to prove this result. We started with a classical query algorithm and a guessing algorithm on this, which is a decision tree and a coloring on these edges. We converted it to a non-binary span program with complexity O of square root of g times t, which is equal to the complexity of the decision tree. And then we converted to a quantum query algorithm whose query complexity is equal to O of square root of g times t. And the question is, what is the time complexity of this query algorithm that we investigated in this work? So as briefly, we have 3 steps. The first step was what I did in my PhD thesis. Was, as I said, converting a decision tree to a non-binary span program. The second step and the third step is to converting this non-binary span program to a quantum algorithm and then implementing this quantum algorithm time efficiently. So we will go through these steps and see what they do. Okay, is there any question?
I guess not.
Okay. Okay, to convert a decision tree to a non-binary span program, we use the idea of SD connectivity. So you may see this SD connectivity span program. So this is the generalized version of the span program for SD connectivity, which is a non-binary span program. And as an example, consider this decision tree that we want to define a non-binary span program for this. So to define this non-binary span program, we have a inner product space, which is the span of V, and V is all of the vertices of this decision tree, and we have some target vectors for actually for every leaf of the tree. We need to have a target vector. So if we reach that target vector or reach that leaf, we say that the output of the function for the input x is equal to the value that that leaf determines. So to define the input vectors for this span program, let's see this example. Let's say that we want to define I sub 3 and I sub 3 and 1, which says that if x3 is equal to 1, we need to make some vectors available. We see in our decision tree and find a vertex that its label is equal to 3. It means that it asks the value of x3. So we have two vertices with the value with x3. One of them is here and the other one is here. In order to define the available vectors for this, we see and it's for the value of I, the value 1. So these two edges should be added to I sub 3 and I. So I add a U2 minus V1, V1 minus U2, which I wrote here, and V3 minus U5, which I wrote here. So I do it for all other edges, and our input vectors will be built like this. So another example is for x3 equal to 0, which we should add these two edges to our available input vectors. So let's say that our input is 1, 1, 1. So we want to evaluate this function f on input 1, 1, 1. So what we do is to start from the root and traverse the decision tree by querying its indices. So in this string, the value of x1 is equal to 1. So I can go through this path, and this vector is available to our is available for us. I can use this vector, which I wrote here. Sorry, this red color is here. And then the value of x2 is equal to 1 again. So I go through here, and the edges, I wrote the edge here, and the third edge is here. And if we add these edges together, we build this T sub U5, which is equal to R minus U5. And this is the target vector, the target vector that is related to this leaf. And it says that the value of f of x is equal to 1. So if I could if I can find a path from a leaf, from a root to a leaf, that leaf determines that the value of f of x for me. And this span program can model this algorithm for me. So is it clear? Okay, this span program that you see here is very similar to the SD connectivity span program that we had before. But the problem here is that the complexity that we find for this non-binary span program is not better than the classical query complexity of this problem. So what we did is to use some idea. Here we make use of the guessing algorithm. In the guessing algorithm, we try to color the edges of the decision tree in a way that there are as few red edges in every pass from root to a leaf. So if we make somehow the weight of these red edges small, or if we make the edges, these red edges heavier than the black edges, we may be able to reduce the complexity of this non-binary SNAP program. So we divided the edges into two sets. The first set is the black edges, and the second edge is red edges. And we give a weight of W sub red and W sub black to all of these edges, which is related to their colors. And using this idea, we get the bundle of square root GT. Okay. So basically, this is the idea that we used here. And what we did is to just divide the edges into two categories, red and black. It may be helpful if we can somehow define more colors or define more weights in our edges and improve this bound. Actually, we did some improvement in this result. I mean, not the bound, but for some problems, we observed that if we vary the weights and we only not depend them on the colors, but depend them on their heights in the decision tree, that may help to improve the query complexity for some functions that I will talk about it later. So is the idea clear till now?
I think so.
Okay. Okay, let's go to the second step. In the second step, we need to convert this non-binary SNAP program to a quantum algorithm. As I said, a quantum algorithm is an alternation between two types of unitaries, and we build it like this. So we define a unitary U, which is the product of two reflections. One of them is 2 pi x minus 1, and the other one is 2 lambda minus 1. Pi of x is defined like this, and this is related to the input x, and somehow play the role of this O of x for us. And this is determined with the I of x, which is the index set of, the pi of x is index set of the available input vectors in our matrix A. And pi is the projection into the kernel of a matrix M that we define here. We put the matrix A that we define for this program here, the matrix A, as I said, is the collection of our input vectors, and I sub 3 should be here as well. And M is related to this is the root of the tree, and these are the leaves of the decision tree. So we put these here, and we form a matrix. We call it M. And our algorithm is based on using this matrix U. So in order to okay, the algorithm is as follows. We define two vectors, phi of x plus and phi of x minus. Phi of x plus is equal to the sum of the ket 0 and ket f of x. And phi of x minus is their difference. So if you see, if we start, the zero cat will be equal to the sum of phi of x plus and phi of x minus, and f of x, which we want to be our output, is equal to difference of phi of x plus and phi of x minus. We show that this phi of x plus that we defined here has a large overlap with the eigenvalue plus one eigenvector of the matrix U that defined in the previous slide. And we also show that the phi of x minus has a small overlap with eigenvalue plus one eigenvector of U. So we can somehow distinguish between two states using the phase detection algorithm. So what we do in our algorithm is to start with the state 0, which is the sum of the phi of x minus and phi of x plus. And we reflect this phi of x minus using the phase detection algorithm. And we somehow convert this state to this state by reflecting this to this. And the output will be f of x. Okay, this is the algorithm that we want to use. We know the query complexity of this algorithm, but we do not know its time complexity. Here we want to implement this algorithm time efficiently. Okay, in order to implement this algorithm time efficiently, we need to do U efficiently. This consists of these two reflections. This first one is easy to implement using two queries to the input, but the second one is the tricky part, which is related to the projection to the kernel of this M. So we try to make this the kernel of this matrix M structured, so we can implement this time efficiently. So in order to do that, what we do is to change this matrix M into some M tilde. Let me start with a simple case where G is equal to 1. I mean, we only have one red edge in any path from the root to a leaf in our decision tree. What we do is to start with a decision tree and its coloring, and we convert it into something, we call it a decision graph. We build M tilde out of this decision graph. And we prove that this M is structured enough, and we can somehow find its kernel and do the reflection about this kernel time efficiently. Okay, I won't go into the detail of the construction, but the construction is very simple. It consists of some local investigation of the decision tree. So in order to do this conversion, we need to be able to traverse the decision tree somehow in its black edges, and we need to be able to build the decision tree locally. I mean, if you're given a vertex B, we should be able to find its neighbors in a constant time or in a logarithmic time. So what we do here is to start with this decision graph that we build all of our decision tree, and we build its kernel, the kernel of M tilde that we build all of this decision graph. And its kernel consists of two types of vectors. Type 1 vectors are associated to red edges here. These vectors are independent and orthogonal to each other. So we can do the reflection about them separately and do the all the reflections in superposition, so it won't introduce a cost for us. The tricky part is for the type 2 vectors, which are related to black edges. So these black edges here introduce independent but not orthogonal vectors in our kernel for matrix MTIL. So what we do is to try to, by adding these extra edges here, we somehow can do this reflection using a Fourier transform. So the Fourier transform can be implemented in time all log and log squared n. So it will add an extra factor of log squared root n to our time complexity. Okay, these are for the case where g is equal to 1, and to do it for greater g's when we have more than 100 edges in our decision tree, we can convert. We can say that this is a union of some trees with one green edge, with one red edge. Sorry. So this is a collection of two decision trees with two red edges. So we can use the same ideas that we had for the case of g equals 1 and implement the algorithm when g is equal to 1, and g is greater than 1 in time O of square root gt times some log 2 sub n, log 2 of n, which comes from the Fourier transform that I talked about. Okay, this is the basic idea, and I won't go further into details since I don't have more time. Let me quickly go into some applications. The first application is to use it for finding a minimum spanning tree in a given graph. So let's say that we are given a graph on some vertices S, A, B, C, D. We have 5 vertices. So we start with a from some node that we call it S, and we use the BFS algorithm, which is the first search algorithm, in which we add the edges to the spanning tree first. This is a part of the decision tree for this BFS algorithm that I draw here. So we should also equip it with a guessing algorithm, which is a color than with its edges. In the guessing algorithm, we always guess that there are no edges in the graph. So we color every edge that that labels yes with red, which are our wrong guesses. So as an example, consider that we're given this graph, and we want to traverse this decision tree to find a spanning tree on this graph. We start by querying the first edge. The first edge is SA. It asks whether S is connected to A, and it says yes. So we take this pass. The next query is SB, which asks whether S is connected to B, and these are connected. So we go through this pass. And now we should ask whether S is connected to C, and the answer is yes. So we go through here and we continue. like this. The next query is SD. If S is connected to D, no. So we go here, and we see the first black edge here. And the last query is AD, and A is connected to D. So we go here, and this is the path that we traverse to get to this leaf, which determines the value of our spanning tree. So as you see, the number of red edges that we see here in our decision tree is equal to n-1. This is because every time that we see an edge in our graph, we connect that vertex to the spanning tree that we built so far, and this shows that we at most we can see a number of n-1 edges, since the spanning tree only has n-1 edges, and the depth of this tree is equal to can be as high as the number of edges in the graph, which is equal to n squared. This shows that the query complexity of the BFS algorithm is O of n to 3/2. And as we prove, its time complexity is equal to O of n to the third 3/2 log squared n. Okay, and we can use this BFS algorithm to design many graph-based for this graph-based algorithm with graph problems, and all of them has the same complexities. By just changing them a little bit, we can design these algorithms and prove the same bound for all of these problems. So let me quickly go through this maximum matching as well. As I said, we need to operate some of the local operations in our decision tree in order to make the implementation time efficiently. But for the maximum matching problem, we couldn't do this. So we couldn't convert our query algorithm into a time-efficient algorithm. If we want to do, I mentioned, are very high, so we don't get any time improvement when.
Leila, are you there still?
Yes, that's it. We guess what she's saying.
We try to apply this method.
Square root speedup.
To the
Leila, can you hear us? The sound is really cutting out now. We haven't been able to hear you for the last minute or so.
maximum matching problem. So we can only prove a query.
Yeah, you were gone.
Can you hear me? Okay,
now we can hear you.
You cannot hear me?
We couldn't, but now we
Hello.
can.
Yeah.
Yeah, now we can hear you. If now is now.
Okay, let me just refresh. Do you have my slides? Yeah, yeah, I can hear you too. So do you see my slides?
And everything's okay.
Okay. Did you hear when I was talking on this slide?
Yeah, that we heard. But when you transition to the next slide, you cut out.
Okay, that's fine. I guess I'm running out of time, but I will be quick. I just said that we couldn't find time improvements in the algorithm that we find for the maximum matching because the local operations that I talked about that we should need to be implement them locally in our decision tree cannot be implemented in time less than O of log squared n. So our query and time complexity increases if we want to implement this algorithm with a trick that we use to implement time efficiently. So we don't have time improvement for the maximum matching. We only have query improvement for this problem. The other example is the oracle identification problem. This is where we use that varying weights that I talked about, the idea of varying the weights of the non-binary span program to improve the bounds that we get for some problems appeared here. So the oracle identification problem is as follows. We are given a set of M strings, which we call it C, and we have query access to some string X, which is an n bit string, and we have the promise that X belongs to this set. And the goal is to identify X, and as it's clear, we want to make less queries as possible. So Kothari solved this problem and determined its query complexity. What he did is to use repeated applications of Grover search, a variant of Grover search, to determine this value of X. And what we did was to using this idea of varying these weights and not just depending them on their color of the edges that the guessing algorithm detects. We own their heights in the decision tree, and we could be able to remove the log n factor that Kothari gets in his algorithm with his repeated application of the Grover search. I should also mention that he removed this log n factor by using some ideas from adversary bond, but here we don't need that much work, and we can straightly remove this log n factor by using this non-binary span program. And this idea is, can be used in every problem that we can have. We will have repeat applications of somehow in our problems. So this is what I wanted to say. If you have any questions, I will be happy to answer. I'm sorry if I had problems with my connection.